In case of graph focus task, we have to also go beyond it and perform something called dedicated pooling operations. This is similar to what we do in CNN, but it has certain differences. We will see what are those differences. What is pooling operation? We discuss filtering operation. It will take graph structure and the feature associated with the nodes and provides us same graph structure, however learned feature associated with nodes. In the case of pooling, we would like to do a little bit different. Why? We cannot use standard pooling because unlike in convolutional neural networks where the grids are well defined, graph structures are typically highly irregular. As we have given example during the previous lectures, for example of molecular structures, which we represent as a graph. Different molecule has a different structure and which is highly irregular. Similarly, other graphs which are available in the literature are also highly irregular, and we cannot predict a priori what will be the structure of particular graph in my data set. Other things which we are interested when it comes to graph focus task is to generate features for entire graph. And here the node features are actually one which are going to be used along with the structure of the graph to create a feature for the graph. And hence we have to also develop a operation which allows us to create a feature for the graph, and where the pooling plays an important role. What pooling does? Pooling operation typically utilize graph structure and feature associated with the nodes. In pooling operation, it takes graph as an input and provides a reduced graph with a less number of nodes as an output. Let's look at here a pooling operation where Fin is the input feature matrix which we have provided. Here we have a input adjacency matrix which we have provided, and we perform a pooling operation. Then we get the output length features and output adjacency matrix. Now here you can see that the adjacency matrix in the output, which is cardinality of the adjacency matrix, is V out, and the cardinality of the set V in are different. Here typically the V out is less than V in. In other words, the pooling operation allows us to change structure of graph. Remember, in filtering, we have never changed. A has gone in, the output is only F out. However, in pooling, it is A in and A out. In addition to that, we also have a input feature F in and the output feature, which are learned feature matrix F out. D out and D in will have the same kind of property which we have seen in a filtering operation. D out will be lesser than the D in terms of size. So it gives some idea about what pooling operation does. Let's look at the pooling operation more graphically. So here I have given the previous graph where we have A in of certain dimension, F in of certain dimension. Remember that cardinality here is this one and cardinality here is this one, or number of nodes, cross number of nodes here is a cross D in is the features. Now we are going to apply pooling operation on this particular graph, and we will see that the pooling operation leads to the output graph with the less number of nodes. So adjacency matrix here will be cardinality of V out cross V out cardinality. F out will be only for those set of nodes, and the D will be different than, the number of features will be different than D in. So here we can see that the structure of graph, which has a 6 nodes and 7 edges, has been changed to 3 nodes and 3 edges. Not only that, you can also see that the feature vector before and feature vector after pooling operation has a different dimensions. So unlike filtering, where the structure remains constant, in pooling the structure is also changing with a feature vector size. As I told you, this relationship holds. It is possible to have this. If equality holds, it is more like a filtering operation. Okay, equality does not hold, and then it's a pooling operation. Now with this, let's look at the node tasks. Typically, we will not use one filter and one pooling operations. What we'll do is we'll use series of graph filters, and along with that, because we are going to use series of graph filters, we are also going to use activation layers to generate features for a particular node. The whole objective here is again same, to learn better features for each node. In a node task, we are interested in generating a better node features, which allows us to predict any task related to the node, downstream task related to node, in a superior manner. So we'll start with the input features. There is a graph filter followed by activation layer. There is another graph filter, activation layer, and we can have L such layers of activation graph filters and L-1 activation layers. Activation operation is denoted as orange and filtering operation is denoted as a brown. Now let's look at how it turns out in terms of mathematical operations. So framework here is the same as I told you. In node related task, we are going to use a combination of graph filters and nonlinear activation layers, which are in a series. Filter, activation layers, filter, activation layers. Okay. There are L graph filters we will use, and correspondingly L-1 activation layers we will use. We will not do any activation for input feature. It will directly go to the graph filters. The output of this particular set of operations will provide us a learnt and better features, and that can be used for downstream task by any other models. In downstream task, depending on the task, we will use appropriate deep learning models or sometimes machine learning models. So here, the filtering operation, let's look at how it looks like. At any stage, ith stage, we'll take the feature, input feature matrix of the previous stage, which is I-1 layers, graph filter layers, which will be dimension of number of nodes cross D I-1, will pass through activation layers, and the output along with the graph structure in terms of adjacency matrix will be passed through the graph filter. Here, The alpha, which is nonlinear activation layer, will do element-wise activation function, and the HI will lead us to a next level filtered or learned features, the output features which are learned features from the previous layer for the ith graph filtering layers, and then that will go to the next activation layer layers, and henceforth. When it comes to graph task, the framework will be little different. In a graph task, what we will have is, unlike node focused tasks, we'll have a graph filters and nonlinear activation layers. However, in addition to that, we will have a pooling layers. Remember that we need to create a good feature vector for a particular graph to perform a graph level task. For example, given a molecular structure, I would like to create a feature vector for that molecular structure, which I can use later on for any downstream task. So here, the combination of graph filters and nonlinear activation layers will be there, but in addition to that, there will be a pooling layer. The objective of pooling layer is to actually pool after a series of graph filtrations and the activation layers operation. The objective here is, in this particular case, the filtering and activation operation are applied to generate better node features. Their concentration or their main objective is to get a better and better node features. They do not worry about the graph level features. However, pooling layers objective is to summarize in a better manner node features and capture high level graph structure information along with the node features. Hence, the combination of both will create a better feature for the graph. And what will be the final output? Final output will be a coarse graph, okay, and sometimes it will be a flattened feature which can be passed to the other models for a downstream task. Depending on downstream task, we will have either coarse graph or coarsened graph and or other feature vector which can be used for a downstream task. So let's look at a graph task. How we can summarize the graph related task in terms of filtering operations, activation layers, and the pooling layers. So here, the input feature will go, as we discussed in a node related task, through a set of graph filters and the activation layers. Graph filter, activation layer, graph filter, activation layer, until some k activation layers. At the end, it will go to the pooling layer P, which will create output feature for that particular block. Here, we are going to use the concept of block. So one block consists of 3 operations: set of filtering operations and activation operations, and finally a pooling operations. And what particular block will do is try to capture graph level information and summarize the node level features. A series of blocks typically are used in a graph neural networks to summarize node feature by generating a more coarsened graphs and getting a better and better learned feature for a particular graph. So this is particular block, and there are multiple blocks in such a manner will create a graph neural network. So a block in a graph neural networks mathematically will have a following operation, where the block B is a set of operations together, or series of set of operations, where we start with A in input adjacency matrix, F in is input node feature matrix, and the output of block is a new quotient adjacency matrix, which basically summarizes the structure, and F out, which summarizes a learnt feature matrix. Here, this particular B, if you look at more closely, will have a filtering operations and the activations operation in a block, where the ith filtering operations will have adjacency matrix. We will have a F I minus 1, which is the feature learnt in a I minus 1th layer, activation function applied on those features. Together, there is a filtering operation and generating a Fi, and there are such a K, such a I layers are there. So, of course, when I say such a I layers of filtering as well as activation layers. Once we have this Fi at the end of the kth layer, this will go to the pooling layer along with F in. Remember that this F in is more or less same here. F in is not changing. So this you can also say as F in. We apply pooling layer, and after pooling operation, we'll get an output which is F out, is a new learned feature vector, and we'll also get A out, which is a new representation of or coarse graphs representation or graph structure representation.